Hi friends, I am Sudarshan. Today we are going to discuss about transformers. Before starting transformers, let us discuss basics which are necessary for understanding a transformer topic. Okay. See, as I told you, before understanding the transformers topic, basics topic I'm just going to cover. This will be useful for us for understanding the transformers topic clearly. Okay. So, see, according to Faraday, the basic requirements for inducing EMF in a conductor are, you can say, according to Faraday's, the basic requirements for inducing EMF are: number 1, set of conductors; number 2, magnetic field; number 3, there should be relative time variation or relative space variation between conductors and magnetic field. Okay, see, let me write here. According to Faraday, the basic requirements for inducing EMF are: number 1, set of conductors; number 2, magnetic field; number 3, there should be relative time variation we can write in short RTV, or relative space variation we can write in short RSV, between conductors and magnetic field, between conductors and magnetic field. See, in a transformer also EMF is induced, where in case of your generator also EMF is induced. So there is difference between EMF induced in transformer and EMF induced in generators. So that is given by Faraday. According to Faraday, the basic requirements for inducing EMF are: set of conductors, and number 2, magnetic field. See, after having conductors and magnetic field, don't expect EMF. See, ultimately third condition is very, very important. There should be relative time variation or relative space variation between conductors and magnetic field, then only EMF will be induced in that conductor. See example, that is indirectly I can say that this third point only we can call like this: EMF induced in the conductor if there is rate of change of flux linkage in that conductor. This is very, very important. Rate of change of flux linkage should be there, then only EMF will be induced in that conductor. Here pi means flux, N means number of turns, N pi means flux linkage, and rate of change of flux linkage should be there, then only EMF will be induced in that conductor. Let us see, if you take example relative time variation, nothing but RTV. Here conductors are stationary. Whereas magnetic field is time variant. So conductors are stationary, magnetic field is time variant. So here rate of change of flux linkage will be there. How? I'll tell you. Before that, yes, because rate of change of flux linkage, EMF will be induced here. That type of EMF can be called as statically induced EMF. So I can write here statically induced EMF. Statically induced statically induced EMF. Statically induced EMF is induced. Static induced EMF is induced. Example, here we can take transformers. If you see clearly in transformer, which type of supply we are giving to the transformer? AC supply. AC supply we are giving to the transformer. Nothing but V1, whatever we are giving to the transformer, that is time variant supply. Nothing but AC supply. So because of that, current taken by the transformer to create some flux in the transformer core, nothing but I mu, is also AC. Nothing but time variant. Flux produced in the transformer core is also AC. Nothing but time variant. So observe clearly, in transformer, which type of supply we are giving to the transformer? AC supply. Nothing but time variant voltage source connected to the transformer. Because of that, current taken by the transformer is also AC, time variant. So flux produced in transformer core is also AC, time variant. You observe clearly here, flux is AC quantity. Then as I told you, for inducing EMF in a conductor, rate of change of flux linkage should be there. So here phi is AC, time variant flux. Rate of change of flux is possible, not possible here? It's possible. So here, therefore, E proportional to d by dt of n pi, rate of change of flux linkage is possible here. So EMF is induced. A type of EMF induced in transformer is called statically induced EMF. Statically induced EMF. And here you have to understand one simple thing here. Whatever EMF induced in transformer, the direction of statically induced EMF which is induced in the transformer is given by Lenz's law. So let me write here. Direction of statically induced EMF. Direction of statically induced EMF is given by Lenz's law. Lenz's law means what? Simply I can write like this. Effect opposes changes in cause. Effect opposes changes in cause. This is only Lenz's law. We'll discuss. Once we start the transformers, we'll discuss about Lenz's law. Just write simply here. Direction of E statically or direction of a static induced EMF is given by Lenz's law. Effect opposes changes in cause. Next, this is about RTV, relative time variation. Now let us discuss about RSV, relative space variation. This one, second one. In relative space variation, conductors are moving. But magnetic field is time invariant, nothing but DC. So we'll discuss after completing transformers and the induction machine when we'll be discussing about alternators, synchronous motors, DC generators, DC motors. There, if you observe clearly, for all those four machines, we will be giving DC supply to the field winding for excitation. We'll discuss in case of your synchronous machine and DC machines. So, as we are giving DC supply to the field winding for excitation, magnetic field produced there is nothing but time invariant magnetic field. So, magnetic field is time invariant, conductors are moving. So, now tell me, in RSV, rate of change of flux linkage is there or is not there. It's this simple. See, as I told you, for statical induced EMF also, how rate of change of flux is possible? Source connected to the transformer is AC, current taken by the transformer is AC, flux produced in the transformer core is AC. So rate of change of flux linkage is possible, EMF is induced. Okay. Now what I am saying is, in RSV, rate of change of flux linkage is possible or not possible? Here, though magnetic field is time invariant, nothing but I can say DC. Though magnetic field is DC, rate of change of flux linkage still it is possible. You may get doubt, sir. In case of static induced EMF, flux is time variant. So d by dt of n pi is possible. Like that we discussed. Now here, though magnetic field is time invariant, that is DC, rate of change of flux linkage still it is possible. How means? Though magnetic field is time invariant, here conductors are moving. Conductors are moving. Because conductors are moving, magnetic field, though it is a time invariant, though it is DC, rate of change of flux linkage will be possible. So that one I will write it as EMF rate of change of flux linkage will be possible. So dynamically induced EMF will be induced here. So we'll write here note. In RSV, in relative space variation, though magnetic field is time invariant, still rate of change of flux linkage is possible because conductors are moving. Because conductors are moving. So rate of change of flux here also possible. Though magnetic field is time invariant, conductors are moving. So these conductors will go and cut magnetic field. Then EMF will be induced. The type of EMF induced because of RSV can be called as dynamic induced EMF. Here dynamically induced EMF is induced. Here dynamically induced EMF is induced. Example. So see, so many things are there. Example means in case of alternator also dynamically EMF is only induced. But perfect example if you want me to say, DC generator. Because in DC generator, armature winding we are placing on the rotor, field winding on the stator. Armature winding is moving because it is placed on the rotor. Conductors are moving. Magnetic field is time invariant. Rate of change of flux will be possible. Though magnetic field is time invariant, because conductors are moving. So the dynamic induced EMF is induced. Example I can write DC generators. Okay. Next, one more note. Here I can write whatever dynamic induced EMF induced here in case of these generators, direction of dynamically induced EMF is given by Fleming's right hand rule. Let me write here. Direction of dynamically induced EMF. Direction of dynamically induced EMF is given by Fleming's right hand rule. Fleming's right hand rule. FR is what here? Fleming's right hand rule. Okay. So here, if you observe clearly, so let me conclude this topic clearly. what I said, according to Faraday, the basic requirements for inducing EMF are conductors, magnetic field. Third one is very, very important. Though conductors are there, though magnetic field is there, without RTB or RSV between conductors and magnetic field, EMF will not be induced. So that's why I'm writing here. There should be relative time variation RTB or relative space variation RSV between conductors and magnetic field. So indirectly, this third point only, how, I mean, because of RTB or because of RSV, rate of change of flux will be possible. So indirectly I can say that there should be rate of change of flux linkage, then only EMF will be induced in a conductor. If you see RTB, relative time variation, where conductors are stationary, magnetic field is time variant, here static induced EMF is induced. Example, transformers. Because in transformer, which type of supply are given to transformer? AC supply, time variant. Current taken the transformer, AC, okay, time variant. Flux produced in transformer core is also AC, time variant. So because flux is time variant, rate of change of flux linkage is possible. EMF will be induced. That type of EMF only I am calling it as a static induced EMF. Example, transformers. And here direction of a static induced EMF is given by Lenz's law. Lenz's law means what? Effect opposes changes in cause. We'll discuss once we'll start the transformers topic. In RSV, conductors are moving, magnetic field is time invariant. Remember, DC supply, DC magnetic field is produced. Though magnetic field is time invariant, still rate of change of flux is possible here, because here conductors are moving. Conductors are moving and magnetic field, though it is time invariant, so rate of change of flux linkage is possible because conductors are cutting. Conductors are cutting your magnetic field, no? So rate of change of flux will be possible because conductors are moving. So that one I wrote here. In RSV, though magnetic field is time invariant, still rate of change of flux linkage is possible because conductors are moving. So here dynamically induced EMF is induced. Example, DC generators. Here note, direction of dynamically induced EMF is given by Fleming's right hand rule. Okay, please note down all these things. Note down clearly. Yeah. Now, As we explained about RSV, dynamically induced EMF, let me tell you principle of a generator here only. Okay, so that will be easy for you to understand. So generator principle. Generator principle. Generator principle. You know, what is the function of generator? It converts mechanical energy. It converts mechanical energy into. It converts mechanical energy into electrical energy. Mechanical energy to electrical energy. Electrical energy. Electrical energy. Okay. See, if you want me to say what is the principle of generator, I'll write like this. No, when a moving conductor, when a moving conductor, when a moving conductor, when a moving conductor curves the magnetic field, when a moving conductor curves the magnetic field, and EMF or current is induced in that conductor. If you observe clearly, when a moving conductor, that means whatever, what is the function of generator? I told you, it converts mechanical energy into electrical energy. Here, moving conductor indicates we are giving mechanical energy to this conductor. When a moving conductor curves magnetic field, then EMF or current is induced in that conductor. EMF or current is the indication that we got electrical energy produced at output. Therefore, here moving conductor indicates mechanical energy, EMF or current indicates electrical energy. If you observe clearly, this is nothing but RSV only. When a moving conductor, yes, conductors are moving, curves magnetic field, yes, magnetic field, time invariant magnetic field, EMF will be induced. Nothing but what is the type of EMF induced here? Dynamically induced EMF is induced here. When a moving conductor curves the magnetic field, an EMF or current is induced in that conductor. So tell me, what is the type of EMF induced because of generator action? Dynamically induced EMF. If you want me to say, see clearly here. Let me take on a north pole is there here. This is what your south pole, north pole and south pole. So because of excitation, what is the definition for excitation? That we'll discuss in case of your synchronous machine. So because of excitation to the field winding, magnetic flux lines are coming from north pole to south pole. These are the flux lines we got. They are flowing, they are traveling from north pole to south pole. And let me take a conductor. Let me take a conductor here. Let me take a conductor. We take a conductor and provide mechanical energy to this conductor. Let me move this conductor in this direction. So that means what the direction of most of the conductor means this one, V. I am just moving conductor in this direction with the velocity how much here? V, small v. And as I told you, this is the direction of your magnetic flux density. And here, you know, EMF or current is induced. When a moving conductor curves the magnetic field, an EMF or current is induced in that conductor. So what I told that EMF induced because of generator action is nothing but EMF because of relative space variation only. And that ED is equals to formula I can write BLV sin theta. Here capital B means magnetic flux density in Weber per meter square or Tesla. Weber per meter square or Tesla. And LE means effective length of the conductor. Effective length of the conductor. See, don't take L means total length from here to here. Please take only length of the conductor which is under the influence of magnetic field. That means how much length falls under magnetic field, that much length only should take. That means from here to here I can say. This much length only should take. This is the only nothing but LE value. Effective length of the conductor or length of the conductor which is under the influence of magnetic field. So, effective length of the conductor, or I can say length of the conductor which is under the influence of magnetic field. This length is in meters. And small v means I am just moving this conductor in this direction, this V. So V means linear velocity of the conductor, in meters per second. And what about theta? Theta is the angle between V and B. Linear velocity and magnetic flux density in electrical degrees. So when a moving conductor causes a magnetic field, an EMF or current is induced in that conductor. That is only dynamically induced EMF. I can write here ED means what here? Dynamically induced EMF in volts. So that ED equals to BLV sin theta. B means magnetic flux density in Weber per meter square. LE effective length of the conductor in meters. Small v means the linear velocity of the conductor in meters per second. Theta, angle between V and B in electrical degrees. And the direction of dynamically induced EMF is given by, I already told you, is given by Fleming's right hand rule. Okay. So here if you want me to discuss about Fleming's right hand rule, as I told you, direction of dynamically induced EMF is given by Fleming's right hand rule. In Fleming's right hand rule, if you observe clearly, so whatever the principle I told here, please tell the same statement like this. When a moving conductor, Fleming's right hand rule, when a moving conductor causes a magnetic field, an EMF is induced in that conductor. When a moving conductor causes a magnetic field, an EMF is induced in that conductor. So thumb means direction of motion of the conductor. That is nothing but your thumb indicates mechanical energy. When a moving conductor causes magnetic field, your forefinger indicates direction of magnetic field. Nothing but your forefinger indicates magnetic energy. When a moving conductor causes a magnetic field, an EMF is induced or current is induced in that conductor. That means center finger or middle finger indicates direction of EMF induced, direction of current induced. Nothing but your center finger or middle finger indicates electrical energy. So let me write here In Fleming's right hand rule, thumb indicates what? Direction of motion of the conductor. Direction of motion of the conductor. Direction of motion of the conductor. Indirectly, I can say that thumb indicates mechanical energy. Mechanical energy. And forefinger. Forefinger indicates direction of magnetic field. Direction of magnetic field. Indirectly, it indicates magnetic energy. Magnetic energy. Magnetic energy. Magnetic energy. And center finger or middle finger indicates direction of EMF or current, direction of EMF or current induced. Nothing but your center finger indicates electrical energy. So thumb indicates mechanical energy, forefinger indicates magnetic energy, center finger or middle finger indicates electrical energy. Okay, please note on this. This portion already you drawn here, so please note down remaining things. Okay, next we'll discuss about since we explained generator principle here, let me explain motor principle here only, so that it will be easy for you to follow. Motor principle, which converts electrical energy into mechanical energy. This only I'm just writing this like this. When a current carrying conductor placed in a magnetic field, when a current carrying conductor placed in a magnetic field it experience force or torque. It experience force or torque. This only I can say indirectly Lorentz force law. Lorentz force law. Lorentz force law. If you observe clearly, when a current carrying conductor, so we are giving electrical energy input to your motor. Here current carrying conductor indicates electrical energy. Okay, input electrical energy. Placed in a magnetic field, it experiences force or torque. Force or torque indicates mechanical energy. Mechanical energy. Mechanical energy. So this is only your Lorentz force law. And here you should understand one thing. Whatever force experienced because of motor action, that is given by Fleming's left hand rule. Direction of force experienced because of motor action is given by Fleming's left hand rule. Fleming's left hand rule. If you see Fleming's left hand rule, so whatever the statement you just told, so tell me this statement once again, like this, Fleming's left hand rule. When a current carrying conductor, see previously while discussing about Fleming's right hand rule for generator, I told like this, when moving conductor causes the magnetic field, EMF is induced in that conductor. So there I told thumb indicates mechanical energy, forefinger indicates magnetic energy, center finger indicates electrical energy. Now I'm asking about motor principle. Because of motor principle, I got force experienced. If you want to know the direction of force experienced because of motor action, so please go for Fleming's left hand rule. In Fleming's left hand rule, whatever the statement, you just tell like this. When a current carrying conductor placed in a magnetic field, it experiences force or torque. So when a current carrying conductor placed in a magnetic field, it experiences force or torque. So please now let me write whatever, first write center finger and middle finger. Center finger or middle finger indicates direction of current. When a current carrying conductor placed in a magnetic field, it experiences force or torque. So center or middle finger indicates direction of current, nothing but electrical energy. Now forefinger indicates when a current carrying conductor placed in a magnetic field. So forefinger indicates direction of magnetic field. Direction of magnetic field, that is your forefinger indicates magnetic energy. And what about thumb? So please tell once again Fleming's left hand rule. When a current carrying conductor placed in a magnetic field, it experiences force or torque. So thumb indicates direction of force experienced. Direction of force experienced because of motor action, which indicates mechanical energy. If you observe clearly, here center finger indicates electrical energy. Previously also in Fleming's right hand rule also, center finger indicates electrical energy only. Forefinger indicates magnetic energy. In previous discussion, Fleming's right hand rule also, forefinger indicates magnetic energy only. Thumb indicates mechanical energy in Fleming's left hand rule. In Fleming's right hand rule also, thumb means mechanical energy only. So ultimately, if you observe clearly, in Fleming's right hand rule or left hand rule, in Fleming's right hand rule, thumb means mechanical energy. Here also thumb means mechanical energy only. Forefinger means magnetic energy in case of Fleming's right hand rule. Here also forefinger means magnetic energy only. Center or middle finger indicates electrical energy in case of Fleming's right hand rule. In case of Fleming's left hand rule also, center finger and middle finger indicates electrical energy only. Okay, please note on this. Okay, note on. FLH means what? Fleming's left hand rule. Right. Next, one more basic thing you should know for understanding our electrical machine subject. See here, very simple. One more basic thing. What is the meaning of cross? Cross means what? Cross means direction of current entering into the board. Direction of current entering into the board. Direction of current entering into the board. Cross means. Or I can say, see, if the current is going into the board, that means indirectly direction of current going away from the observer. See, cross means direction of current entering into the board or direction of current going away from the observer. So I can write like this, or direction of current going away from observer. Now what about dot? Dot means what? Direction of current coming from the board. Coming from the board means what? It is coming towards the observer. So let me write here, direction of current coming from the board or direction of current coming towards the observer. Please note on this also. Cross means current direction of current entering into the board or going away from the observer. Dot means direction of current coming from the board or coming towards the observer. Yeah. Now see, I think by this information only you should understand what is meant by Faraday's first law. and Faraday's second law. Faraday's second law. Faraday's second law. Faraday's second law. I think we just whenever we start the subject today, first topic only. According to Faraday, the basic requirements for inducing EMF are the conductor's magnetic field, either there should be RTV or RSV between conductor and magnetic field. That is only Faraday's first law. How EMF is induced is given by Faraday's first law. How EMF is induced is given by Faraday's first law. How EMF is induced? If there should be conductors, there should be conductor, there should be magnetic field, and there should be relative time variation or relative space variation between conductor and magnetic field. There should be conductor, there should be magnetic field, there should be RTV or RSV between conductor and magnetic field. That is only your Faraday's first law. Faraday's second law means what? The magnitude of induced EMF is given by Faraday's second law. How much EMF is induced is given by Faraday's second law. So let me write here. Faraday's first law means EMF induced in a conductor, EMF induced in a conductor, if there is relative time variation or relative space variation between conductors and magnetic field. Indirectly, Faraday's first law says how EMF is induced. That is given by Faraday's first law. That is, there should be RT or RSV between conductor and magnetic field. Then only EMF is induced in the conductor. That is only Faraday's first law. Faraday's second law means how much EMF is induced. How much EMF is induced. That is only of Faraday's second law. That means indirectly I can say that the magnitude of induced EMF is given by Faraday's second law. That means we already discussed it. There should be I told you EMF will be induced in a conductor if there is rate of change of flux linkage. That is only. That is, the magnitude of induced EMF is given by Faraday's second law. That is E proportional to d by dt of n pi. That means E is equals to what? N d by dt. E proportional d by dt of n pi, or E equals N d by dt is the magnitude of induced EMF induced in a conductor. This is only your Faraday's second law. Very simple. How EMF is induced is given by Faraday's first law. How much EMF is induced is given by Faraday's second law. If there is RTV or RSV between conductor and magnetic field, EMF will be induced. That is only Faraday's first law. And the magnitude of induced EMF, E proportional to d by dt of n pi. That means E equals to N d pi by dt is the magnitude of induced EMF. That is given by Faraday's second law. Okay. Please note down this one. Yes. Next we'll discuss what are the let me discuss the transformers. There we'll discuss what are the features of transformers. We'll start with the transformers next session. Okay. Next session we'll start with the transformers. So before that, this much information is necessary for us for understanding your transformers topic.